Generally speaking, when we talk about compilation, we mean the process of turning our high-level source code into a binary artifact, which can be executed on a machine or used at runtime.
Let's take a look at the main type of such artifacts. We can roughly subdivide binary artifacts into a few categories. Lower-level binaries such as bootloaders, firmware, kernel and kernel modules. At startup, two stages of bootloading take place. The boot ROM, which initializes the hardware, and the bootloader, which loads the operating system kernel. Once the operating system is loaded into RAM, it takes over execution. Or there could be another step for an embedded device. An embedded system software based on FreeRTOS project running directly on a microcontroller together with the connected devices, without a full general purpose OS. Hosted binaries such as executable programs, shared libraries, static libraries, relocatable object files and core dumps. Most of them are used by the operating system to execute program functionality. They depend on system calls and use them to access registers or memory. Specialized binaries such as GPU programs. Some binaries are designed to run on specialized processors rather than the CPU, such as GPU shaders or compute kernels. They are used to render graphics or perform non-graphical, compute-intensive tasks such as scientific computing or artificial intelligence. On the other hand, there are some high-level programming languages that are not compiled into a binary file. Instead, they are executed at runtime by specific software. For example, if you launch a Python script, it will be handled by the Python interpreter, which itself is a compiled binary running as a process. And here we can see our Python process, it's the interpreter running our script. In this video series we will mostly be interested in hosted binaries that can be executed directly by the operating system.
So what is a binary from this perspective? In this sense we can say that a binary is a set of binary data organized according to a defined layout, so a loader or execution environment can understand its contents, identify different parts of the program and their rules.
In this video series we will mostly be exploring the ELF file format, which stands for Executable and Linkable format. It's used for executable files, libraries, object files and core dumps. Standalone binaries such as firmware can also be compiled into ELF initially, mainly for debugging purposes. This format is the default for most Unix-like operating systems, including Linux, FreeBSD, QNX, Solaris and many others. It also widely adopted in embedded systems and game consoles. Platforms like Nintendo and Sony PlayStation often use ELF under the hood. ELF originated with Unix System V or System 5 Release 4 in the late of 1980s. Nowadays the standard and its documentation are maintained by the Linux Foundation, and the document is available online. Through this series we will be referring to this specific document. It contains the full details about ELF structure, section types and the other internal components. Of course, some other operating systems use their own binary formats. Windows uses its own portable and executable file format. Mac OS uses its own Mac object file format. These formats have different layouts and underlying principles for how they organize program data. Eventually, the compilation is quite a complicated process that contains several steps, and today we will take a look at them. In a large project we would likely use tools like CMake, which help us organize source files, define linking properties, set desired compilation flags, specify target platform and architecture, program pre- and post-compilation actions. In Unix-like systems, CMake produces a makefile which contains compiler-specific sets of parameters. But at the end of the day, all of this boils down to a set of parameters we feed into the compiler. But to build a simple program with just a single source file, we can call a compiler directly, specifying source files and options. As a result, we will get an executable binary file, which can be executed directly by the operating system. The compilation process is not monolithic by design. Instead, it's split into several phases.
You might ask, why do we need all these intermediate steps? Why not just go directly from, for example, C++ to a binary? Well, for practical reasons.
Let's look a bit deeper. First of all, modern compilers support multiple programming languages. Each of them provides different features and abstractions, and turning every one of them directly into binary machine code would be extremely complicated and inefficient. So instead, compiler translate them into a common intermediate representation and assembly, from where the toolchain can manipulate and optimize the code in a unified way. On the other end of the pipeline, we also have a wide range of platforms and architectures we may want to support, such as x86, ARM, RISC-V, Power. So as you can see, there are many possible combinations of input language and output architecture. That's why splitting the compilation process into separate phases makes sense. It allows the compiler to remain flexible, portable and efficient across all the combinations. To get our code successfully compiled, it must of course be free of syntax and semantic errors. We would also like it to be free of logical mistakes and ambiguities that could lead the program to run with undefined or unpredictable behavior. To help with that, we can follow the C++ core guidelines, a set of best practices created by experts in the C++ community. In addition, we can use third-party static code analysis tools to keep our code clean, consistent and compliant with the coding standard we have adopted. It's worth mentioning that several industry standards define best practices for coding style and compliance, helping ensure software quality, safety and maintainability. Some widely used standards include MISRA, stands for Motor Industry Software Reliability Association. Primarily used in the automotive industry, these standards enforce safe coding practices and reduces the likelihood of software defects. AUTOSAR, based on MISRA but tailored specifically for automotive software architecture and modern C++ usage. DO178C, a standard used in aviation software development to ensure compliance with strict safety and certification regulations. JSF stands for Joint Strike Fighter, a set of guidelines developed for military and defense systems, focused on robustness, maintainability and long-term reliability. Now let's have a look at the first phase of the pipeline, the preprocessor. We can ask the compiler to perform only the preprocessing step using -e flag. Let's write the preprocessor output to a new file. If we look at the result, we will see that the compiler has expanded all include and define directives and stripped out all comments from the source code. In our example, the line include EOStream is expanded into the full contents of that library header. The macro define test message is also fully expanded wherever it appears in the code. At this stage, the compiler frontend analyzes the high-level code for syntax errors and semantic errors. In addition to errors, the compiler may also generate warnings. These highlight potential issues that don't prevent compilation but might indicate bad practices or unintended behavior. The warning system is configurable. Developers can enable or disable specific warning categories. Focus on things like unused variables, implicit type conversions, unreachable code, etc. It's also common, especially in safety critical or performance sensitive projects, to treat all warnings as errors so that no issue goes unnoticed. If syntax and semantics checks pass, the next step is the generation of the intermediate representation. An intermediate representation is a bridge between high-level languages like C and C++ and low-level assembly. It allows the compiler to analyze, optimize and transform the code in a structured, architecture-neutral format. At this stage, no new syntax errors appear. The code has already passed all parsing stages. The compiler now focuses on optimization. Some additional warnings may be triggered, especially if optimization flags are enabled. So the purpose of this phase is to get the code as efficient as possible before converting it into architecture-specific machine instructions. We can ask the compiler to stop after generating code, so not going further to the assembly stage, and emit human readable code, intermediate representation code, or to generate binary intermediate representation compact bit code. It's important to note that intermediate representation is part of a compiler's backend design, and different compilers use their own intermediate representation technologies. In this example I use Clang compiler, which produces LLVM intermediate representation, a well-known modular and portable format. But other compilers such as GCC or Intel, they may have their own internal representations, but they all serve the same purpose, providing a bridge between high-level language construct and low-level assembly that will be generated for specific target architecture. Next, let's take a look at the assembly phase, where the compiler translates the optimized intermediate representation into assembly code. At this stage the code becomes architecture specific, since assembly language operates directly with registers and instructions defined by a particular processor architecture. We can explicitly generate assembly code using this command. It will produce a file with assembler code which contain architecture-specific assembly code. By default, the compiler generates assembly code for the host architecture, the system on which the compiler itself is running. To specify the platform and the architecture explicitly, we can use target flag. Its format looks like this. This tells the compiler to generate code for a specific target triple, which includes CPU architecture, vendor, operating system and environment. This mechanism is essential for cross-compilation, building code on one platform for execution on another. Now let's compile our code and look at how the assembly output reveals the target architecture. Here we can see registers and instructions specific for x86 architecture, and here we can see registers and instructions specific for ARM architecture. The next step is turning the output from the previous stages into object files, also known as translation units. It's common practice to keep one source file per translation unit. This setup is customizable, but it's worth keeping it flexible and well structured, so that the build system can recompile only those object files whose source files were modified in the previous step, without rebuilding the entire project. In large-scale projects this approach is essential and can save a significant amount of time during incremental builds. We can generate an object file by adding the parameter C. This tells the compiler to preprocess, compile, assemble, but not to link, and as a result we will get an object file. Let's take a look at the result using the file utility. You will see something like this. Let's break this down. ELF, executable and linkable format. 64-bit LSB. LSB stands for least significant byte first, meaning the file uses little endian byte ordering. x86-64, the architecture the code was compiled for. Relocatable indicates that the file is not yet fully linked and can be combined with others by the linker. Not stripped. File still contains debug symbols and metadata, which are useful for debugging. And finally, we come to the finalizing phase of the compilation pipeline, linking. At this stage, all the object files and static libraries are merged together into a single binary. One of the most important goals of this phase is resolving references to functions and variables. If a function is declared in one translation unit and used in another, the linker connects those objects together. If symbols are undefined at the object file stage, the linker tries to resolve them, either from our object file or from linked libraries. While performing dynamic linking, the linker ensures that all symbols are resolved and record references to shared libraries in the ELF binary in so-called dynamic section. Dynamic section contains a list of required shared libraries, symbol table of unresolved function and variable references, a procedure linkage table to handle runtime lookups. Compilers like Clang and GCC automatically link against standard libraries. This behavior is part of a default toolchain configuration, so there's no need to specify these libraries manually in simple cases. For example, in our Hello World application we used stdcout, which is implemented in libstdc library, and we can confirm this by running readelf-d. The output will show that the program is linked against that library, even though we did not explicitly request it in the compilation command. GCC and Clang do not perform linking themselves. Instead, they usually invoke an external linker behind the scenes, such as LD or LLD. We can observe this behavior with the free hash flag. This points out all the internal steps the compiler takes, and near to the end we will see the line like calling the linker. That's the linker being called, and we can clearly see it participating in the compilation pipeline. As a result of linking, especially dynamic linking, we can now see, using readelf-d, the dynamic section which lists the required shared libraries, using readelf-s, the dynamic symbol table with unresolved symbols, and using readelf-r, relocation entries used for runtime resolution. Dynamic linking is a huge and fascinating topic. It's one of the most impactful inventions in software architecture, enabling code reuse, smaller binaries and modular software design. And we will definitely explore it much deeper in future videos. Now we have our final binary, an executable file. Let's now overview what is inside of our compiled binary artifact. We can refer to the System5 application binary interface specification. Here we can find the formal specification of ELF object file format. As we know, there are three main types of object files: relocatable, executable, and shared objects. Chapter 4 describes the structure of ELF object files and fields common to all object types. And Chapter 5 describes how executable and shared object files are loaded into memory and how dynamic linking works. The ELF file in essence contains of the following components: ELF file header, program header table, and section header table. Here we can see hints about fields layouts and how many bytes every field takes. ELF header contains entry information about the file, like magic number, which is a hexadecimal number which in ASCII means ELF, operating system, type of a binary file, machine architecture, start and sizes of program headers and section headers, etc. So basically the ELF header acts as a roadmap describing how a file is organized. By the way, the header file with C structure definitions of ELF structures in Unix-like systems like FreeBSD or Linux we can find under user include directory. And the detailed description of each field and its purpose we can find in the standard document. Each object file contains a section header table which contains information about all the sections in the file, and each section is described by a corresponding section header entry. Section header has fields such as section name, section address, section offset, section size, etc. And looking at our executable file here, we can observe the section header table. Here we have sections such as dynamic symbol table, it is used by the dynamic linker, read-only data, that typically contribute to a non-writable segment in the process image. In it contains initialization code executed before main function on a program startup. Text contains text or executable instructions of a program, debug symbols, and other sections. A program header table, if present, tells the system how to create a process image. So executable files and shared libraries contain a program header table, and relocatable object files typically do not. In next episode dedicated to program execution, we will explore this topic deeper.